Altan oluyor. Ne yapıyor? Çekiyor.
Hi, I'm Unmanned. I'm the captain of ITUNOM. It will be team's third year and my second year in the competition. I'm studying computer engineering for 3 years and I'm responsible for object detection and classification. And I will lead the team in the mission demonstration.
I'm Enes. I'm an aeronautical engineering student. It's my first year in both university and ITUNOM team. I'm responsible for the mechanics of the UAV and I'm also the safety pilot of the team.
I'm Ertuğrul. I'm the captain of the avionics sub-team and this is my senior year at Control and Automation Engineering and this is my third year at competition and in my team. I'm responsible for autonomous flight and obstacle avoidance. During the mission demonstration, I'll be looking after a ground control station.
I am John and I am the second year of aeronautical engineering. This is my first year in ITUNOM and I am the designer of the vehicle and the captain of the mechanic team. In race week, my duty will be setting up the vehicle and doing the pit stop.
I'm Sertan. This is my second year in electrical engineering and first year at ITUNOM UAV team. I have been interested in electronics and programming before, but it's my first experience and UAV. I'm responsible for taking data from JAT server and make them ready to use. And I will oversee the interoperability process during the time of flight.
I am Aleren, the captain of the software sub-team. This is my second year of computer engineering and the first year with ITUNOM. I am responsible for object detection, classification and localization. During the flight, I will be looking after the image processing computer.
I'm Resul. I'm sophomore at Electronic and Communication Engineering. This is my first year at ITUNOM team and also this competition. I'm responsible for communication network and image transfer jobs.
I'm Furkan. I'm third year electronic and communication student. It's the first year in the team. I'm responsible for avionics system and RF systems. Also, during the exhibition, I will control the antenna.
My name is Melih. I am sophomore student at ITU Control and Automation Engineering. I am a member of avionics sub-team. I will direct the antenna during the competition.
I am Oğuzhan. I am Control and Automation Engineering student. It's my first year at the university and the team both. As the avionics sub-team member, we are working together with Melih. We are working on autonomous flight and obstacle avoidance. During the mission demonstration, I will be assisting ground control station operator.
Our vehicle's properties have been determined according to maximize our performance in AUVSI SUAS competition. Two have 8 Tiger MN 4014 motors and 18-inch propellers. In order to optimize flight time and flight performance, we had decided to use 6S 22,000 mAh battery in our vehicle.
This is Tulpar. I will talk about this avionics system. First of all, we use as our autopilot XR2, which controls the autonomous flight and the gimbal, also the air drop system. And this is our GPS module, which is attached with the Raspberry Pi 3. Raspberry Pi 3's job is that is controlling the photo imaging process and also the imaging process accuracy. We add extra battery to power the balloon.
We, as ITUNOM team, are very assertive on missions. We work hard on all missions and took precautions for all possible problems. We will accomplish autonomous flight, target recognition and localization, which is autonomous P2, actionable intelligence, off-axis target imaging, emergent targets, interoperability and static obstacle avoidance. We have some problems on moving obstacle avoidance, but we believe that we will solve them and accomplish that mission perfectly too.
So far, we have conducted 47 autonomous flights. Each flight takes approximately 15 minutes. We can conduct fully autonomous flights. Our safety pilot gets control of vehicle if only the vehicle gets into an extraordinary condition. In autonomous mode, we can determine vehicle speed and waypoint radius. One of the advantages of using multicopters is you can determine waypoint accuracy sensitivity. So if we decide 5 feet radius sensitivity, we get 5% error. The only thing that can decrease our sensitivity is wind. With medium strong wind, we get at least 90% accuracy. And this is an acceptable rate for us.
An advantage of high waypoint accuracy, it makes obstacle avoidance easier. This year we will attempt only stationary obstacle avoidance. When we set correct waypoints for the missions, UAV can follow waypoints easily. To determine avoidance algorithm, we decided to use simple algorithms instead of complex algorithms as RRT and RRT star. For determining avoidance algorithm, we decided to use simple algorithm instead of complex algorithms as RRT and RRT star. In our algorithm, first we take waypoints, then we simplify to make it workable for software. When we get obstacles, firstly we control our determined waypoints which intersect with obstacles. If there is an intersection, algorithm generates a new waypoint next to it. Then we check it for being in flight area. If it is out of the area, we determine new waypoint next to older waypoint with different angle. Then we make same process until we get correct waypoint. After that, algorithm makes some comparison and determine which line parts of waypoints intersecting with obstacles. When we determine these coordinates, we generate new waypoints that have distance from obstacle with 120% of obstacle's radius, and it has the average angle of line respect to obstacle. Then we check whether it's in the flight area, and if it's in the no-flying zone, then we check whether it's in the flight area, and if it's in the no-flying zone, we generate new waypoints in the opposite direction. Then we connect all waypoints to each other.
Our major system includes a camera, a US computer, a 5 GHz antenna and a GPS. This year, in order to increase the imaging performance, we chose Sony a6000 DSLR camera instead of Samsung Galaxy K Zoom. Sony a6000 has 24.3 megapixel exmo APS sensor, and we are using the camera with 1650 lens. In our system, captured images are sent instantly to the ground contrast station, and the images are processed with very short delays, averagely 1 or 2 seconds. Thus, image size is crucial. In order to prevent delays during the image transfer, we use camera in fine mode. Tests show that average photo size is 6.4 in this mode. The image size has nice quality and the transfer speed is good as we need. For a major system, we built our own system consisting of the software and network substructure. The software is written Python Flask. It's used for web framework. The network is provided by Bolt M5 linked to Raspberry Pi and NanoStation wirelessly connected to the access point on Bolt M5. We have written our own file transfer protocol to get the best camera performance, and we have created some security protocols for file transfer to ensure inter-network security. We have also redesigned the web page to get full control over the camera, such as ISO shutter value and other essential functions.
For detection and classification, we create our own software which is developed with open source image processing library OpenCV. Before starting detections, some precautions must be taken. Sunlight or other light sources might affect targets and lead to misdetections or misclassifications. To reduce such effects, image is blurred with equal weighted kernel. Other precaution we take is for asphalt and concrete areas. Cracks on these areas may form shapes which may lead to misdetections. To avoid that, such areas are removed from the image.
To find the region of interest, Kini edge filter is applied to certain channels of BGR and HSV color spaces. To shortly describe the process, optimal area interval for targets is specified during our tests. Using the information, large and small areas are eliminated. Contours with the same color of grass are also eliminated. The color is also specified during tests. After the processing, the program is left with 2 or less possible contours. Comparing outputs of each channel, the program decides whether there is a possible target. If there is, Then the classification process starts. Detected target is cropped from the original image. To recognize shape, alphanumeric and their colors, some pre-operations are required. The external boundary of target is drawn on a black image and filled with white color. This image is used for shape recognition. For alphanumeric recognition, similar procedure is applied to internal boundary of target. Applying some bitwise logical operations on obtained images and the original image, color values of shape and alphanumeric are obtained. To briefly explain the shape and alphanumeric recognition system, they use k-nearest neighbor algorithm. Alphanumeric templates are created in different font sizes and font families so that the recognition is adapted to different appearances and yields reasonable outputs for incomplete alphanumeric extraction. At the end, result of classifications and the cropped image are sent to interoperability system.
Our localization algorithm is starting in our UAV. By taking picture, our computer takes the position and direction of the UAV from the GPS model it has, then sends it with the picture has been taken. In ground station, if we detect an object in picture, we are looking to the position in the picture, and we are finding the position of the object according to our vehicle. Then we take the difference vectors and take the projection to the north and east vectors. Then we convert them to latitudes and longitudes. If we add difference vector to our position, which is we obtained from GPS and vehicle, so we can find the exact position of the object.
For the airdrop system, we use a cube-shaped plexiglass and a servo motor connected to the opening car. We deliver the load with a drop parachute. We did get encouraging results from the tests. We attempted 8 tests. At first, 2 of them, the delivery didn't survive and approximately 30 feet away from the target. We did some fortification and straightened the parachute in order to provide safety of the delivery. Then we managed to hit near the bullseye for 6 times. Our success rate is 75%.
We test our system several times in different places, be able to get the best results. Our first test was hover test, in purpose of deciding which propeller we going to use, 16 inches or the 18 inches. We make our test first with the 16 inches and it made 22 minutes only, but we do it again with 18 inches, they make 27 minutes and a half. So we decide to continue with the 18 inches, but 27 minutes is not enough for the real exhibition, so we are decide on the making pit stop. Also, data transferring is tested with these systems on application, but results were not close to our expectation. So we upgraded the firmware and results were getting 15% better. We test the system again with the real photographs which is taken from the Alpha 6000 by Raspberry Pi. In 1000 feet distance, speed is 2.5 megabyte per second. In 2000 feet distance, speed is 1.5 megabyte per second. In 3000 feet distance is only 0.8 megabyte per second. Results show that we need to continue the transferring after the landing by Wi-Fi. At autonomous flight, we test DJI, PixArt and PixArt 2. PixArt 2 and DJI's performance were great, but PixArt 2 is open source, so our last decision is PixArt 2. Image processing program is tested on previous years' competitions photos. Test results can be categorized as color detection is 90%, shape detection is 75%, average of all shapes. Shape accuracy is approximately 18%. Alphanumeric accuracy is 65%. In test, UAV's average speed is observed as 35 feet per second. At maximum speed is observed 43 feet per second. At 200 feet altitude, camera can absorb 328 feet log a line. So if you fly at 200 feet altitude and take in 5 seconds period photo, it's ensured that any region is photographed at least once. Thanks to that, probability of missing a target is minimized.